So if we look at this McConkey agar plate, um, like I said, this plate is selective and differential. So the crystal violet and the bile salts in the plate are only going to allow gram-negative bacteria to grow. So if you put any type of gram-positive bacteria on this plate, they will instantly shrivel up and die because they're not able to grow in this plate. So if you see any growth on this plate, you automatically know you're looking at some type of gram-negative bacteria. However, different types of bacteria, gram-negative bacteria that is, will grow different colors based on how they interact with the media. So if you put a gram-negative bacterium in here and it's able to ferment the lactose and use the lactose as an energy source, it will grow bright pink. And that's what we're seeing here with E. coli. E. coli is a known lactose fermenter. So what happens is when you put the E. coli bacterium in here, it's going to ferment the lactose, which is going to cause acids to be released, which is going to cause the pH of the plate to go down, which is going to cause that pH indicator to turn bright pink. And that's why we're seeing bright pink growth for E. coli here. However, if you put a gram-negative bacterium in here that did not ferment lactose, it would grow because it's gram-negative and it can grow on this plate, but it wouldn't grow bright pink. It would just grow like a clear color on top of the plate, so the plate would kind of just look the same color. And the reason why it would not grow bright pink is because the lactose wouldn't have been fermented, which means the acids would not have been released, which means the pH would not have changed, and that means the pH indicator wouldn't change. So only gram-negatives grow. However, they can grow different colors based on if they use the lactose or not. If they use the lactose, they grow bright pink. If they do not utilize the lactose, they just grow colorless, which is basically like a clear color on top of the media, so the media would look very similar to the color that we see kind of down in this bottom part. So the next plate is the EMB plate, or eosin methylene blue. The EMB plate is used to isolate or grow fecal coliforms. Fecal coliforms are bacteria commonly found in feces like E. coli. This plate is selective and differential again. So it's selective because it only allows certain types of bacteria to grow, but differential because the bacteria that do grow will grow different colors based on how they interact with the media. So as far as the contents of an EMB plate, it does contain peptone, which you don't need to worry yourself with. Peptone is just a source of carbon and nitrogen for the bacteria, so just kind of nutritional source for them for their essential nutrients. I do want you to know what type of sugars they have, though. The EMB plate actually contains two sugars, lactose and sucrose. This is different because when we did the mannitol salt agar, it only had mannitol as a sugar source. When we did the McConkey agar, it only had lactose as the sugar source. So the EMB plate is unique in the sense that it actually contains two sugars, lactose and sucrose. And these sugars do tell us something about bacteria. Typically, bacteria that are commonly found in feces, like E. coli, they're going to use the lactose. And typically, E. coli found in feces is a normal thing. It's the most common bacteria found in feces, and it doesn't always mean that it's pathogenic. It's just kind of the normal biota that's found in feces, and it does commonly use the lactose. However, Salmonella bacteria are often pathogenic, meaning they can cause disease, and Salmonella typically are going to use the sucrose as a source of fermentation as an energy source. So the EMB plate does have two different types of sugars, and different bacteria use different sugars. Typically, the kind of normal biota fecal bacteria like E. coli are going to use the lactose, whereas the more pathogenic, dangerous bacteria such as Salmonella, they're going to use the sucrose. So the EMB plate, like I said, it's selective and differential. So we'll talk about why it's selective first. So the EMB plate only allows gram-negative bacteria to grow. Gram-positive bacteria are going to be inhibited. Because remember, we're trying to grow bacteria that are commonly found in the feces. Feces was once in the gastrointestinal system, which is mainly just gram-negative bacteria. So again, we only want to grow those gram-negative bacteria, so we need to inhibit the growth of gram-positive. So in the EMB plate, there's eosin Y dye and methylene blue dye. The eosin Y dye and the methylene blue dye are what make the plate selective because they're going to inhibit the growth of gram-positive bacteria. So gram-positive bacteria cannot grow on an EMB plate for that reason, because of the eosin Y and the methylene blue. So if you see any growth on this plate, you know you're looking at some type of gram-negative bacterium. Now, the gram-negative bacteria that grow on the plate will grow different colors based on how they utilize the sugar sources, but at least we know they are gram-negative. So here we have all gram-negative bacteria because we do see growth. However, growth does occur in different colors based on how they interact with these sugar sources. So most bacteria that are gram-negative and grow on this plate and ferment the lactose, they are going to grow this dark purple to black color. So most gram-negative bacteria that ferment lactose will grow dark purple to black. An exception to the rule is E. coli. E. coli are gram-negative, so they grow great on this plate, and they do ferment lactose, so you would think that they would grow this dark purple to black color, but they're unique in the sense that they typically grow this metallic green color. So metallic green is an indication typically that you are looking at E. coli. So most bacteria that grow on this plate and use the lactose, they will grow dark purple to black. However, E. coli that grow on this plate, E. coli do ferment lactose, however, they grow metallic green. If you're working with a bacterium that's gram-negative and will grow on this plate, but it does not use lactose or uses the sucrose, it will just grow a clear color on top of the plate. So if it's gram-negative and it does not use lactose or it uses sucrose, it will grow just this kind of clear color. So the next test is called the citrate test. So this test is used to see if a bacterium can use citrate as its sole source of carbon. So when we do the citrate test, the only source of carbon in the test tube is citrate. And if the bacteria can use citrate as a carbon source, they'll be able to grow and survive. However, if they can't, then they will obviously not be able to grow and divide and they'll die off. So when we do this test, what we're doing is we're looking to see if our bacteria have this enzyme called citrate permease. If your bacteria have this enzyme called citrate permease, that means they're going to be able to use citrate as their sole source of carbon, which they need carbon as an essential nutrient in order to grow and divide. However, if your bacterium does not have the citrate permease enzyme, that means they're not going to be able to break down the citrate to use it as their sole source of carbon, so they would not survive within the media. So when you do a citrate test, what you're really doing is looking to see, does your bacteria have the citrate permease enzyme, yes or no? If it does, that means it can use citrate as its sole source of carbon. If it does not, that means it's not able to use citrate as its sole source of carbon, so it must need something else for a carbon source. So over here we have a citrate test. So typically the citrate test starts out as this kind of green test here. This is just kind of a normal one, and it's in a test tube. And really all you have to do is add a small sample of bacteria into the citrate test. You have videos of this test in D2L, but it is kind of a solid agar that's in a test tube, and it kind of runs on a slant so that you can add the bacteria to the slant. So if your bacteria have the citrate permease enzyme and you add them into the citrate test, they're going to be able to use citrate as a carbon source and continue to grow and divide. However, if your bacteria do not have the citrate permease enzyme and you add them into the citrate agar test tube, they're not going to be able to use citrate as a carbon source, which means they're not going to be able to grow and divide and they die off. So how do we know if the test actually kind of produced positive or negative results? Typically, it's indicated by a color change. So with the citrate test, if it turns blue, that's a positive result. If it stays green, that's a negative result. Remember, it was green to start with. So if it just stays green, that's negative. That means your bacteria does not have the citrate permease enzyme, and your bacteria are not able to use citrate as a sole source of carbon. However, if it turns bright blue, which is what we see here, that's an indication that yes, your bacteria has the citrate permease enzyme, and yes, your bacteria can use citrate as their sole source of carbon. So how it works is these test tubes actually have pH indicators too. Just like the plates have pH indicators, the test tubes have pH indicators. However, with the plates, typically the pH would go down to cause the color change to happen. So remember with the mannitol salt agar, when that pH went down, it turned yellow. With the McConkey agar, when the pH went down, it turned bright pink. Well, with these test tubes, for the color change to happen, the pH actually is going to go up. So how it works is if I have a citrate test and it starts out green, that's just what its normal color is, and I put a bacterium in there that has the citrate permease enzyme, that enzyme is actually going to break down and utilize citrate. And when that happens, it's going to cause ammonia to be released. And that's going to cause the pH to actually go upwards. And when the pH goes up in these test tubes, the pH indicator turns bright blue. So when it turns bright blue, that's an indication that yes, citrate was utilized as a carbon source and our bacteria have that citrate permease enzyme. But if you put a bacterium in here that did not have that enzyme, then citrate would not be broken down, which means the ammonia would not be released, which means the pH would not go up and the color would not change. It would just kind of stay that green color. So the majority of the time, if you see blue, that's positive, and green, that's negative. There are cases where you will put a bacterium in here that does have the citrate permease enzyme. So it should break down citrate, it should cause a color change to happen, and it should cause the test tube to turn blue, but for whatever reason, it doesn't. And sometimes that can be due to incomplete incubation. So you can't always just look at the test tube and say, oh, it's green, it's negative. Look at it and see if you actually see growth, because if it's still green but you see bacteria growing, that can still be a positive result. We would definitely always like to see a nice blue positive result, but that doesn't always happen. So if it's green and there's no growth, that's definitely like a hard negative. But if you look at it and it's green and there's growth, that's still considered positive. We would ideally like it to be blue, but sometimes that doesn't always happen. And typically we do inoculate these with inoculating needles just to get a small amount of bacteria on there, because if you get too much, you might incorrectly read the results as having growth when really you just kind of added a big clump of bacteria. But predominantly for your purposes, with the procedures that we're doing and the results that we're reading, you'll be able to just kind of look at the color and record results. So just keep in mind, green is negative unless there's growth, whereas blue is positive.